So here in this example, we can look at integrating the tan x function. Notice that tangent can be written as sine over cosine. And in doing it like this, we can notice that substitution might become useful here. In particular, I noticed that we can take u equal to cosine x in the denominator, and then its derivative, which is negative sine x, will be a multiple of the expression that we have in the numerator. So that suggests here that doing a substitution of that form will be useful. And then the derivative, negative sine x, will leave us with a negative sign when we do the substitution. And so our integral transforms into the integral of 1 over u du, and that would be just negative ln of u. And so we would have negative ln of cosine. And in fact, we can bring the negative inside the logarithm here, because that would be the same as cosine x to the negative 1 power. So it would be 1 over cosine x. Of course, we know that can be written as secant. Okay, so here we have the integral of tan x is ln of the opposite value of secant x. Now, if we ever forget this, we can always work it out this way, but this is one that I would suggest you guys remember. Now let's think about how to deal with the case when we have a logarithm of a general base, say base b. One nice thing is that we can always rewrite log base b in terms of the natural log. So in this case, the derivative of log base b of x we know would be ln of x over ln of b. And since we're here dividing by a constant, we can take that out of the derivative. So we're doing 1 over ln of b times the derivative of ln x. And we know ln x, of course, the derivative is 1 over x. Okay, so I can write the derivative of log base b of x as 1 over x ln b. Let's practice that with this example here, log base 10 of 2 plus sine x. So we'll have 1 over ln of 10 because we got a base of 10 here. But because it's 2 plus sine x inside the logarithm, we'll have 2 plus sine x times ln of 10. But then we're going to apply the chain rule here because we've got the derivative of 2 plus sine x will be multiplied. Of course, that's just cosine x. So here I'll write this as cosine x over 2 plus sine x times ln of 10. In fact, here we can think about now how to take the derivative of a general exponential function. But here our trick will be to think of the b to the power of x function in terms of the e to the x. So in other words, b to the power of x, here let's think of it this way, b to the power of x, I can rewrite this as e to the ln of b power to the x. right? Because b can be written as e to the ln of b. So this would be the same as e to the x times ln of b. So if I'm taking the derivative of b to the x, I can think of this as the derivative of e to the x times ln of b. And we know how to deal with the derivative of e. It's just e to the x times ln of b times the derivative of x times ln of b. In this case, the derivative of x times ln b is just a constant times x. So we're left with that constant ln of b. And I can then return e to the x ln b back to b to the x. So it's b to the x times ln of b. So let's practice that below here. If I've got the derivative of 10 to the power of x squared, well, that'll be 10 to the power of x squared times ln of 10. But then we've got x squared, so we're going to multiply by the derivative of x squared, which is 2x. So there's a little bit of chain rule in there as well. Now let's think about doing antiderivatives. Essentially, we can use the work that we've shown here to show that the derivative of b to the x is b to the x ln of b. So if I'm going to do an antiderivative of b to the x, well, we can think of it as dividing out the ln of b if we want to do the antiderivative. So in other words, we'll do 1 over ln of b times b to the x. Okay, so when we're doing the antiderivative of b to the x, we're going to divide by ln of b. So for instance here, if I want to do the integral from 0 to 5 of 2 to the x, this would be 1 over ln of 2 times 2 to the x, and then we'll evaluate from 0 to 5. So of 1 over ln of 2 times 2 to the power of 5 minus 2 to the power of 0. So that's going to be 32 minus 1 is 31. So I'm left with 31 over ln 2. Suppose now I'm differentiating some very complicated expression like this. So here I'm going to exemplify this technique of logarithmic differentiation in order to simplify the process of taking a derivative when we see something like this, which contains an expression that would require us to use both product rule and quotient rule, as well as some chain rule as well. So all of these products and quotients and exponents can be simplified when we apply a logarithm to it. So in the first step of the process, I'll start by applying natural log to both sides of the equation. So let me list out the steps that I'm going through over here. So the first step is we're going to apply the natural log to both sides of the equation. So on the left-hand side, we'll have ln of y. On the right-hand side, we'll have ln of this complicated expression, x to the 3 over 4, square root of x squared plus 1, over 3x plus 2 to the power of 5. So before I take any derivatives, though, now I want to use the properties of logarithms that allows me to expand this expression out completely. So we'll use properties of logarithms to expand the expression completely as far as we can go. So on the left hand side we state ln of y. On the right hand side we'll notice we've got a product there, x to the 3/4 times square root of x squared plus 1. So we'll split those up into a sum of logs. And then minus the log of 3x plus 2 to the 5th that we have in the denominator. Okay. We can even go a little bit further by taking out the powers. So we've got the power of 3 over 4. Here there's like a power of 1/2 that we can take out. And then here we can take out the power of 5. So now we'll have ln of y on the left side equals 3 over 4 ln x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. Okay, so that's actually made it a lot simpler now for taking a derivative. Now I no longer have to think about dealing with quotient rule or product rule. In fact, I can just do each of these terms separately. So that'll be the next step, would be to differentiate both sides. Notice we're gonna solve for y prime implicitly because we have ln of y. So now we're going to differentiate each side. So it's like I'm applying d dx to both sides of the equation. So over here we'll have 1 over y times y prime, because we're doing implicit differentiation there, so there's a y prime multiplied. And then over here we'll have 3 over 4 times ln of x, which would be 1 over x when we take the derivative, plus here we'll have 1/2 1 over x squared plus 1 times 2x there, because we're doing the chain rule, minus 5 times 1 over 3x plus 2, and then times 5, or sorry, times 3. The derivative of 3x plus 2 is 3. Okay, and then a final step would be then to multiply y to the other side. So I've got y times all this stuff here. I'll clean it up a little bit as we go. Notice here the 2's cancel. And then the final step would be to replace the original y. So putting this original y in for y here. So that leaves me with the final answer, which looks like this. So we've got the original x to the 3/4 square root of x squared plus 1 over 3x plus 5, sorry, 3x plus 2 to the 5 times all this stuff. So you see the last couple steps there was we found y prime implicitly, and then we replace y with the original function. Okay, so here's a breakdown of those steps. We took the natural logarithms of both sides of the equation and used the properties of logarithms to simplify, differentiate both sides implicitly with respect to x, and then solve the resulting equation for y prime.